Imagine the moment after the Big Bang, not an explosion in space, but the birth of space itself. No stars, no planets, not even atoms. Just a seething ocean of energy, hotter than anything we can conceive, expanding faster than thought. And yet, even in that perfect, formless fire, something was already turning. Not because something pushed it, not because a hand set it in motion, but because the universe, from its very first breath, could not be still. We often picture the beginning as chaos, but it wasn't random. Beneath the frenzy was a hidden order, a silent law waiting to reveal itself. That law would one day spin galaxies into spirals, fling planets around suns, and even twist the tiniest particles into perpetual motion. It's called angular momentum, and is why nothing in the cosmos, not a speck of dust, not a black hole, not you, ever truly sits at rest. But how could rotation emerge from pure symmetry? If the early universe was smooth, uniform, and isotropic, meaning it looked the same in every direction, where did the first twist come from? The answer lies not in force, but in chance, in imperfection, in the quiet tremor of quantum uncertainty that rippled through the newborn cosmos like a whisper in a cathedral. Right after the Big Bang, during a phase called cosmic inflation, space itself stretched exponentially, growing from smaller than a proton to larger than a galaxy in less than a blink of an eye. During this expansion, microscopic quantum fluctuations, tiny variations in energy density, were blown up to cosmic scales. These weren't errors, they were seeds. And where matter later gathered around these denser patches, gravity began to pull. But gravity alone doesn't create spin, it pulls straight inward. So why didn't everything just collapse into motionless clumps? Because nothing in the universe is perfectly aligned. Even the tiniest offset, say a cloud of gas drifting ever so slightly off-center from another, creates torque. Think of two dancers reaching for each other but missing by a hair. Instead of colliding head-on, they graze, and that near miss sends them circling. In the early universe, every particle was part of such a near miss. No two bits of matter fell toward each other along a perfectly straight line. There was always a slant, a skew, a whisper of sideways motion. And that sideways motion, however faint, was enough. Once set in motion, that rotation couldn't be undone. Not because of magic, but because of a deep conservation law written into the fabric of reality. Angular momentum must be conserved. In empty space, with no friction, no brakes, no external twist, whatever spin something has, it keeps. Forever. Or until it shares it with something else. So when the first hydrogen clouds began to collapse under their own weight, they didn't just shrink. They spun faster, like an ice skater pulling in their arms. That spin flattened them into disks. And from those disks, stars were born. Around those stars, planets formed. And those planets, in turn, carried the memory of that first cosmic wobble. This isn't poetic metaphor. We see it in the data. The cosmic microwave background, the afterglow of the Big Bang, shows temperature variations that map the density ripples from inflation. Computer simulations of structure formation, using only known physics and those initial fluctuations, naturally produce rotating galaxies, orbiting planets, and swirling gas clouds. No extra ingredients, no divine nudge. Just gravity, motion, and the unbreakable rule of angular momentum. What's astonishing is that this same principle applies whether you're watching a hurricane spiral over the ocean or a quasar blaze at the edge of time. Rotation isn't an accident. It's the universe's default setting. Stillness is the anomaly, the fleeting illusion of calm between motions. And And here's the most humbling part. You're made of atoms forged in stars that spun for billions of years. The iron in your blood, the calcium in your bones. They were once part of a rotating stellar core, flung into space by a supernova that itself was shaped by spin. Your body carries the echo of that first twist after the Big Bang. You are not just in the universe, you are of its motion. So when you look up at the night sky and see the slow arc of stars wheeling overhead, don't think of them as distant lights on a dome. Think of them as partners in a dance that began before time had meaning. A dance that started not with a bang, but with a turn. And that turn, infinitesimal, inevitable, eternal, is why everything, from the smallest particle to the largest supercluster, moves not in lines, but in curves. Not in stillness, but in orbit. The universe didn't choose to spin. It simply couldn't do otherwise. Picture a room so vast it has no walls, so empty it contains nothing. Not air, not light, not even time as we know it. Now imagine that in this void, two specks of energy appear. They're drawn to each other by gravity, the universe's quietest pull. If they were perfectly aligned to dead center, no deviation, they'd crash straight together and vanish into stillness. But they never are. Never. Even in the smoothest, most uniform beginning, there's always a sliver of misalignment. And that sliver is where motion is born. This is the secret origin of spin, not from a shove, not from a command, but from the universe's gentle refusal to be perfectly symmetrical. In the first fractions of a second after the Big Bang, the cosmos was a near-perfect fluid of particles and radiation, seething with energy. Yet hidden within that apparent uniformity were tiny random imbalances, quantum ripples imprinted during inflation. These weren't flaws, they were possibilities. And where matter later pooled around these slightly denser regions, the stage was set for motion. But gravity alone pulls inward, it doesn't twist. So how did rotation emerge from pure attraction? The answer lies in what physicists call tidal torques. Imagine three particles floating in space. Two are close, the third is farther away. The distant particle tugs on the pair, but not equally. Its pull is stronger on the nearer one. This uneven force creates a torque, a rotational nudge. In the early universe, every clump of matter felt the gravitational tug of every other clump. And because the distribution wasn't perfectly spherical or centered, those tugs rarely canceled out. Instead, they added up to a net twist. This process didn't require planets or stars, just matter and gravity in an imperfect arrangement. Computer models of cosmic structure formation show that even in a universe starting from near-perfect smoothness, these tidal interactions naturally generate angular momentum in collapsing regions. The spin isn't imposed from outside, it's inherited from the large-scale structure of the cosmos itself. A proto-galaxy doesn't decide to spin, it must. Spin because the gravitational field it grew up in was lopsided in just the right way. And once that spin began, it couldn't be erased. In the vacuum of space, there's no friction to slow things down. No air resistance, no surface to rub against. So whatever angular momentum a cloud of gas acquired during its collapse, it kept and amplified. As the cloud shrank under gravity, conservation of angular momentum forced it to spin faster, like a figure skater drawing in their arms. This isn't just theory, we see it in action. Young stellar objects, still gathering mass from their surroundings, are surrounded by rotating disks of gas and dust, protoplanetary disks spinning at speeds dictated by the angular momentum they inherited from their parent cloud. What's profound is that this angular momentum isn't created, it's redistributed. The total amount in a closed system stays constant. When a star forms and spins one way, the leftover material in its disk spins the same way, preserving the original twist. When planets later coalesce from that disk, they orbit in the same plane and direction because they're all dancing to the same ancient rhythm. Even more astonishing, the direction of spin in galaxies across the sky appears random at first glance. But on the largest scales, subtle correlations have been detected. Galaxies separated by hundreds of millions of light years sometimes show aligned rotation axes, hinting that their spins were imprinted by the same primordial tidal fields that stretched across the infant universe. It's as if the cosmos left fingerprints in the way things turn. This ghost of motion past is why no object in space falls straight down. Everything falls around. Because from the moment matter began to clump, it was already carrying a memory of the universe's first asymmetry, a whisper of sideways motion that refused to die. That whisper became a whirl. The whirl became a disk. The disk became a solar system. And in time, it became us. So when you watch a leaf spiral down from a tree or water swirl down a drain, you're not just seeing local forces at work. You're witnessing a pale echo of the tidal torques that stirred the primordial soup 13.8 billion years ago. Rotation isn't something the universe added later. It was baked in from the start, not as a feature, but as a consequence of being real, of having structure, of existing in a world where perfect symmetry is not just rare, but impossible. The universe didn't need a reason to spin. It only needed to be slightly uneven. And in that unevenness, all motion was born. A single grain of stardust, adrift in the cold dark between galaxies. It's smaller than a bacterium, made of carbon and silicon, forged in the heart of a dead star. Alone, it seems insignificant, just another speck in an ocean of nothing. But this grain isn't alone. It's surrounded by trillions like it, all drifting through a vast cloud of gas, mostly hydrogen, left over from the Big Bang. And though no one is watching, no music plays, this cloud is already beginning to dance. Not because it wants to, not because something told it to, but because gravity quiet, patient, relentless, has begun to pull. And in that pull, a waltz begins. Gravity doesn't shout. It whispers, it gathers. Over millions of years, the cloud grows denser in some places than others, thanks to those ancient quantum ripples we spoke of earlier. Where density rises, gravity strengthens. And where gravity strengthens, matter flows inward. But remember, nothing falls perfectly straight. Even the tiniest deviation, a particle drifting a hair to the left, another nudged by a passing photon, means the collapse isn't radial, it's lopsided. And lopsided collapse spins. As the cloud contracts, it begins to rotate faster. Not because anything is pushing it, but because angular momentum must be conserved. Think of it like this. If you're holding a spinning bicycle wheel and you pull your arms in, the wheel spins quicker. The same happens to a collapsing gas cloud. As it shrinks from something wider than our solar system down to the size of a star, its rotation accelerates dramatically. What was once a slow drift becomes a whirl. But here's where gravity performs its most elegant trick. It can't pull everything into a single point. Why? Because spin fights back. As the cloud spins faster, centrifugal force pushes material outward perpendicular to the axis of rotation. Gravity pulls in, spin pushes out. And where these two forces balance, a disk forms. A flat, rotating plane of gas and dust, like a cosmic vinyl record spinning in the void. This is the birth of order from chaos. A sphere becomes a disk. Random motion becomes organized flow. And in the center of that disk, pressure and heat build until suddenly nuclear fusion ignites. A star is born. But the story doesn't end there. The disk remains, swirling around the newborn star like a cradle. Within it, dust grains collide, stick, and grow. Pebbles become boulders, boulders become planetesimals, and planetesimals become whirls. And because they all formed from the same spinning disk, they orbit in the same direction, in nearly the same plane. That's why all the planets in our solar system circle the sun counterclockwise, and why their orbits are so neatly aligned. This isn't unique to us. We've observed over 5,000 exoplanets around other stars, and nearly all orbit in flat coplanar systems, just like ours. The Atacama Large Millimeter Array in Chile has even captured images of infant planetary systems, their disks glowing with the heat of formation, dark gaps carved by newborn planets still sweeping up material. These aren't just pictures. They're snapshots of gravity's waltz in real time. But the dance doesn't stop at planets. Stars themselves often come in pairs, or even triples, locked in gravitational embrace. Binary stars orbit each other, sometimes so closely they exchange matter, their surfaces nearly touching. In some cases, one star dies and becomes a neutron star or black hole, and the pair continues its dance, now with one partner invisible, detectable only by the way it tugs on its luminous companion. These orbits can last billions of years, their rhythm set by the same initial twist that started in a collapsing cloud long ago. And even when stars die, the waltz continues. When a massive star explodes as a supernova, the explosion isn't perfectly spherical. Asymmetries in the core, driven by rotation and magnetic fields, send the remnant hurtling through space like a cannonball. Some neutron stars spin hundreds of times per second, their beams of radiation sweeping past Earth like cosmic lighthouses. We call them pulsars, and their precision rivals atomic clocks. Yet they're the collapsed cores of stars that once danced in a disk of gas. What's beautiful is that this entire process requires no conductor, no choreographer, just gravity, motion, and time. The universe doesn't plan orbits, it stumbles into them. Every swirl, every curve, every looping path is the natural outcome of matter trying to fall inward while carrying a memory of sideways motion from the dawn of time. So the next time you see a time lapse of stars arcing across the night sky, remember, you're not watching lights fixed on a dome. You're watching partners in a gravitational ballet that began in darkness long before Earth existed. A ballet that turns chaos into rhythm, dust into planets, and silence into light. And at its heart is a simple truth. Gravity doesn't just pull things together, it teaches them how to dance. You've seen it 1,000 times. Earth circling the sun, the moon tracing its path around us, satellites gliding silently overhead. We call them orbits. But what if I told you they're not really moving in circles at all? What if I told you they're falling, constantly, endlessly, and just keep missing? That's the secret Isaac Newton uncovered when he watched an apple drop. He didn't just see something fall to the ground, he imagined it falling forever. He pictured a cannon on a mountain, so tall it rose above the atmosphere. Fire a cannonball slowly, and it arcs down and hits the earth. Fire it faster, and it travels farther before striking the ground. But fire it fast enough, about 17,000 miles per hour, and something magical happens. The cannonball falls toward Earth, yes, but the Earth's surface curves away beneath it at the same rate. The cannonball never lands. It's in orbit. Orbit isn't about floating, it's about falling with style. And that style is dictated by a perfect balance between two things, speed and gravity. Too slow and you crash, too fast and you escape. But just right and you loop forever, caught in a gravitational embrace that never tightens, never loosens. This is why astronauts float inside the International Space Station. Not because there's no gravity, there's still about 90% of Earth's gravity up there, but because they and the station are in freefall together. They're plummeting toward Earth at the same rate, so relative to each other, they appear weightless. It's like being in an elevator whose cables snapped. For a brief, terrifying moment, you'd float inside the cabin. Orbit is that moment stretched into eternity. But orbits aren't always circles. In fact, perfect circles are rare. Most orbits are ellipses, slightly stretched ovals, because nature loves imperfection. Johannes Kepler discovered this in the early 1600s by studying the motion of Mars. He found that planets don't move at constant speed. They speed up when closer to the Sun and slow down when farther away. The Sun sits not at the center of the ellipse, but at one focus off to the side, so the planet's distance changes throughout its year. Earth, for example, is closest to the Sun in early January, not summer, proving that seasons aren't about distance but tilt. This elliptical truth applies everywhere. Comets whip around the Sun in long, narrow ellipses, spending centuries in the outer dark before diving close enough to sprout glowing tails. Binary stars trace ellipses around their common center of mass. Even galaxies orbit each other in vast, slow ellipses that take billions of years to complete. And orbits can be stacked, nested, layered like Russian dolls. The Moon orbits Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way. And the Milky Way itself is falling toward the Andromeda Galaxy, not in a straight line, but on a trajectory that will bring them into a slow-motion collision in about 4.5 billion years. A dance of two spirals merging into one. But here's the deeper wonder. Orbits are stable, not because space is empty, but because gravity is predictable. Unlike friction or air resistance, gravity doesn't sap energy from a system, at least not significantly over short timescales. In the vacuum of space, an orbit can persist for eons with almost no change. That's why we can predict eclipses thousands of years in advance, or slingshot spacecraft past Jupiter with millimeter precision. The laws governing orbits are so reliable they feel like destiny. Yet orbits aren't eternal. Over immense timescales, even they decay. Tidal forces, those same gentle tugs that gave galaxies their spin, can transfer angular momentum between bodies. The Moon is slowly moving away from Earth, about 1.5 inches per year, because Earth's rotation transfers energy to the Moon's orbit through ocean tides. Eventually, if the Sun didn't swallow us first, the Earth and Moon would become tidally locked, always showing the same face to each other, orbiting in perfect sync. And in extreme gravity near black holes, Einstein showed that orbits behave strangely. Mercury's orbit, for instance, doesn't quite close. Its ellipse slowly rotates around the Sun, a phenomenon called precession. Newton couldn't explain it. But general relativity did. Mass warps space-time, and orbits follow the curves in that fabric. Near a black hole, space-time is so twisted that stable orbits only exist beyond a certain distance. Closer in, and even light can't maintain a path. It spirals in, vanishing beyond the event horizon. So, an orbit is more than a path. It's a conversation between mass and motion, between curvature and velocity. It's the universe's way of saying you can fall forever as long as you're moving sideways fast enough. And in that falling, you create rhythm. You create time. You create the cycles that let life arise. Seasons, days, years, all born from the simple act of missing the ground. When you look up at the moon tonight, don't think of it as hanging in the sky. Think of it as falling, gracefully, endlessly, around a planet that's itself falling around a star, which is falling around a galactic center. All of it part of a cosmic cascade of motion that began with a whisper of asymmetry in the first moments of time. Orbit is not escape. It's surrender to gravity, to geometry, to the elegant truth that sometimes the only way to stay aloft is to keep falling. Zoom in past the clouds, past the atmosphere, past the crust of the earth, down through rock and magma into the heart of an atom. You're now smaller than anything visible, smaller than a virus, smaller than a molecule. You're in a realm where the rules of falling and circling no longer apply. And yet, everything here is still moving, spinning, whirling. But not in the way you think. For decades, we've been taught that electrons orbit the nucleus like planets around the sun. It's a beautiful image, neat, orderly, familiar. But it's wrong, deeply, fundamentally wrong. And the truth is far stranger, far more mysterious, and far more beautiful. Electrons don't orbit. They exist in clouds of probability. They don't trace paths. They occupy states. And while they carry something we call spin, they aren't actually spinning like tiny tops. The word is a relic of early quantum theory, a metaphor that stuck even though it misleads. So if electrons aren't circling, why do we still talk about atomic orbits? Because the illusion is powerful. When scientists first probed the atom in the early 1900s, they saw that electrons could only have certain energies, like steps on a ladder, not a ramp. Niels Bohr proposed that electrons moved in fixed circular orbits, jumping between them by absorbing or emitting light. It worked mathematically, and it explained the colors of hydrogen's glow. But it was a temporary scaffold, not the final building. The real picture emerged with quantum mechanics. In the mid-1920s, Erwin Schrödinger wrote an equation that didn't describe where an electron is, but where it's likely to be. The solutions, called orbitals, are not paths, but shapes, spheres, dumbbells, cloverleaves. An electron in the lowest energy state around a hydrogen nucleus isn't whizzing around. It's smeared out in a fuzzy sphere, with the highest chance of being found close to the center, but no definite position at all. It's not moving in space the way a planet does. It's delocalized, existing in many places at once until measured. And yet, this electron still has angular momentum. Not from circling, but from its quantum state. Physicists call this orbital angular momentum, and it's tied to the shape of the orbital. A spherical s orbital has 0, a dumbbell-shaped p orbital has 1 unit, a cloverleaf d orbital has 2. This isn't motion in the classical sense. It's a property of the wave itself, like the twist in a corkscrew of probability. Then there's spin, the other kind of angular momentum electrons carry. Every electron has spin 1/2, a fixed amount that never changes, but don't picture it rotating. If an electron were a tiny ball spinning fast enough to produce that much angular momentum, points on its surface would move faster than light, impossible under relativity. So spin isn't motion, it's intrinsic. It's just there, like mass or charge. A fundamental feature of what an electron is. And yet, this quantum spin has real consequences. It's why chemistry works. The Pauli exclusion principle. No two electrons can occupy the exact same quantum state relies on spin. Electrons pair up with opposite spins, allowing atoms to build complex electron shells. Without spin, all electrons would crowd into the lowest orbital, and atoms beyond hydrogen couldn't form. No carbon, no oxygen, no life. Even stranger, when you place atoms in a magnetic field, their energy levels split based on spin orientation. A phenomenon called the Zeeman effect. This isn't theory, it's used daily in MRI machines to image the human body. The quantum whisper of spin echoes in hospitals, in labs, in the very structure of matter. So if nothing is orbiting at the atomic level, why does rotation appear at larger scales? Because quantum angular momentum adds up. When trillions of atoms align their spins, as in a magnet, their tiny contributions create a macroscopic field. When gas clouds collapse to form stars, the random quantum motions of particles average out into a net classical rotation. The quantum world doesn't vanish, it coheres. Like raindrops joining a river, individual uncertainties flow into collective certainty. This is the bridge between the invisible and the visible. The spin of an electron isn't the same as the spin of a galaxy, but both obey the same conservation law. Angular momentum, whether quantum or cosmic, cannot be created or destroyed. It can only be transferred, transformed, shared. And here's the deepest irony. The reason planets orbit in flat disks is ultimately tied to the quantum nature of light and matter. Photons, particles of light, carry angular momentum too. When a collapsing cloud radiates heat, it emits photons that carry away some angular momentum, allowing the cloud to flatten further. Even the way dust grains stick together in protoplanetary disks depends on electromagnetic forces governed by quantum spin. So while electrons don't circle like planets, the universe still turns. Not because everything mimics the solar system, but because angular momentum is a universal currency, spent differently at every scale, but never counterfeit. The next time you hear electron orbit, remember it's a ghost of an old idea. The truth is quieter, stranger, and more profound. Electrons don't race around nuclei. They hum in place, vibrating with potential, their angular momentum woven into the fabric of reality itself. They don't move in space. They define what space means for matter. And in that quantum whisper, the cosmos finds its rhythm, not through motion alone, but through the silent, persistent presence of spin. Look up on a clear night, away from city lights, and you might see the Milky Way, a hazy river of stars arching across the sky. It's beautiful, serene. But that band of light is not static. It's a storm. A whirlpool of 100 billion stars, all circling a center we cannot see, bound by gravity we cannot feel, spinning so slowly that a single orbit takes 230 million years. And our sun. It's just one passenger on this grand carousel, halfway out from the middle, riding the spiral arm like a leaf on the cosmic current. But galaxies don't spin in isolation. They are nodes in a vast, invisible scaffold, the cosmic web, a sponge-like structure of filaments and voids that stretches across the observable universe. This web was seeded by those same quantum ripples from the Big Bang, stretched to galactic proportions by inflation. Over billions of years, gravity pulled matter along these filaments, like water flowing down grooves in stone, gathering into clusters, groups, and solitary islands of stars. And as matter flowed in, it didn't fall straight. It came in at angles. It collided. It twisted. That's how galaxies got their spin, not from internal engines, but from the geometry of the universe itself. In the 1970s, astrophysicists realized that a galaxy's rotation axis often aligns with the filament it formed within. Imagine a thread of dark matter, a cosmic spine stretching across space. Gas flows along it, pooling it into sections. As it collapses, the tidal forces from neighboring structures torque the cloud, setting it spinning perpendicular to the filament. So a galaxy doesn't just spin randomly, it spins in response to the shape of the void around it. Its rotation is a fossil imprint of the large-scale structure that birthed it. This is why spiral galaxies, like ours, rotate in flat disks. The initial cloud had net angular momentum, and as it collapsed, conservation of that momentum flattened it into a plane, just like the protoplanetary disks around young stars. But elliptical galaxies tell a different story. They're blobby, featureless, and often show little coherent rotation. Why? Because they form through violent mergers. Galaxies crashing into each other, their orderly spins scrambled into chaotic motion. In those collisions, angular momentum isn't lost. It's redistributed, randomized, turned into the random orbits of stars tumbling through a stellar swarm. Yet even in chaos, rotation leaves traces. Some giant ellipticals show faint rotation in their outer regions, relics of their last major merger. And dwarf galaxies, small, faint companions to giants like the Milky Way, often orbit in planes, suggesting they were once part of a single rotating structure before being torn apart. The universe remembers its motions, even when shattered. Now consider the scale. The Milky Way spins at about 130 miles per second at our location. But that speed doesn't drop off as you move outward, as Newtonian gravity would predict. Instead, stars far from the center orbit just as fast as those closer in. This was one of the great mysteries of the 20th century, until astronomers realized most of a galaxy's mass isn't in stars or gas, but in something invisible, dark matter. This ghostly substance doesn't emit light, but it exerts gravity. It forms a vast spherical halo around galaxies, extending far beyond the visible disk. And it's this halo that dictates the rotation curve, the relationship between orbital speed and distance. Without dark matter, spiral galaxies would fly apart. With it, they hold together, spinning like gyroscopes in the dark. But here's the haunting part. We still don't know what dark matter is. We see its gravitational effects on galaxy rotation, on light bending, on the motion of galaxy clusters, but it remains elusive. Yet its presence ensures that galaxies keep turning, that their stars stay bound, that their spiral arms wind and unwind over eons. And those arms, they're not fixed structures. They're density waves, ripples in the disk, like traffic jams in space. Stars move in and out of them, slowing briefly as they pass through, triggering bursts of star formation. The arms glow not because the same stars stay there, but because new stars are constantly being born in the wave's wake. So the spiral is an illusion of persistence, a pattern that endures while its paths flow through it. Even more astonishing, galaxies don't just rotate, they precess. Like a wobbling top, their spin axes can shift over time due to gravitational tugs from neighbors. And in the dense cores of galaxy clusters, galaxies orbit the common center of mass, tracing vast ellipses over billions of years, their own internal spins untouched by the larger motion. So a galaxy is not a single object spinning in place. It's a hierarchy of motions. Stars orbiting the center, star clusters orbiting within the disk, gas clouds collapsing into new stars, all embedded in a dark matter halo that itself may be slowly rotating. And this entire system is falling toward the Great Attractor, a gravitational anomaly in the direction of the Centaurus constellation, part of an even grander flow in the cosmic web. When you gaze at the Andromeda Galaxy through a telescope, you're not just seeing light from 2.5 million years ago. You're seeing a twin to our own Milky Way, spinning in the same kind of dance, born from the same cosmic blueprint. And in a few billion years, our two galaxies will merge, not in a crash, but in a slow gravitational embrace that will scramble both disks into a single, larger, elliptical galaxy. The stars won't collide, they're too far apart, but their orbits will be rewritten. The rotation we know will fade, replaced by a new kind of motion. Yet even then, angular momentum will be conserved. It won't vanish. It will be shared, transformed, woven into the new galaxy structure. Because in the end, a galaxy's spin isn't just about motion, it's about memory. It's the fossilized echo of the first asymmetries in the universe, ripples that grew into rivers of stars, all turning, all falling, all remembering the shape of the void that gave them birth. So the next time you see a photo of a spiral galaxy, don't just admire its beauty. Listen. In its arms, in its core, in the dark halo that holds it together, you can hear the whisper of the cosmic web, telling a story that began before stars existed and will continue long after they're gone. In the deepest void between galaxies, where not even a single photon has passed for eons, in the heart of a black hole, where time itself seems to stop, at absolute zero, where all motion should freeze, is there true rest? Is there anywhere in the universe that doesn't turn, doesn't drift, doesn't hum with some hidden motion? We like to imagine stillness, a frozen lake at dawn, a stone in the desert, a silent room at midnight. But these are illusions, local, temporary, human-scale tricks of perception. Zoom in, and the lake's surface trembles with molecular vibrations. The stone's atoms jiggle with thermal energy. Even in the quietest room, electrons race through wires, air molecules collide, and your own blood pulses with motion. True stillness, complete absence of motion, doesn't exist in our universe, not because of chaos, but because of law. Because motion, in one form or another, is woven into the very definition of what it means to be. Take the vacuum of space. It looks empty. But quantum field theory tells us it's seething. Virtual particles blink in and out of existence, borrowing energy from the void for fleeting moments, governed by the uncertainty principle. This isn't speculation, it's measurable. The Casimir effect, where two metal plates in a vacuum are gently pushed together by the pressure of these quantum fluctuations, proves it. Even nothing is restless. Now consider absolute zero, the temperature at which all classical motion should cease. We've gotten within billionths of a degree of it in labs, yet even there, atoms don't stop. They settle into their quantum ground state, but they still possess zero-point energy, a minimum irreducible jitter mandated by quantum mechanics. An electron in a hydrogen atom at absolute zero still has kinetic energy. It doesn't orbit, but it doesn't sit still either. It exists in a blur of potential, humming with motion that cannot be silenced. What about black holes, the ultimate sinks of gravity, where matter is crushed to infinite density? Surely there, at the singularity, all motion ends. But we don't know. Our laws of physics break down there. General relativity predicts a point of infinite curvature, but quantum gravity, still incomplete, suggests something else, perhaps a Planck scale core vibrating with quantum foam, or a loop of space-time spinning eternally. And even if the center is still, the black hole itself often rotates. Most do. Kerr black holes, named after Roy Kerr, who solved Einstein's equations for spinning ones, drag space-time around them like water circling a drain. This frame dragging is so powerful near the event horizon that nothing can remain stationary. Space itself is forced to turn. Stillness isn't just impossible, it's forbidden by geometry. Even light, which has no mass, carries angular momentum. Circularly polarized photons spin as they travel, transferring torque to objects they strike, a phenomenon used in optical tweezers to rotate microscopic particles. So even pure energy turns. What about the universe as a whole? Does it rotate? Observations say no, or at least not detectably. The cosmic microwave background is isotropic to 1 part in 100,000. If the entire cosmos was spinning, we'd see a preferred axis, a twist in the sky. We don't. So on the larger scale, the universe appears non-rotating. But that doesn't mean it's still. It's expanding, stretching, carrying galaxies apart like raisins in rising dough. Expansion isn't motion through space, it's space itself growing. Yet it's still a form of change, of dynamism. And here's the philosophical twist. Stillness might not even be a coherent concept in a relativistic universe. Einstein taught us there's no universal. Now, no fixed background against which to measure rest. Motion is always relative. You can only say something is moving relative to something else, so absolute rest has no meaning. Even if you float alone in intergalactic space with no stars in sight, you're still moving relative to the cosmic microwave background. In fact, we measure Earth's motion by the slight Doppler shift in that ancient light warmer in the direction we're heading, cooler behind. We're never at rest, not truly. Even in death, motion persists. When a star dies and becomes a white dwarf, its electrons are packed so tightly they resist further collapse. Not by heat, but by quantum pressure. Degeneracy pressure born from the Pauli exclusion principle. Those electrons aren't orbiting, but they're moving at a significant fraction of the speed of light, confined yet restless. In neutron stars, protons and electrons are crushed together into neutrons, which themselves spin and flow in superfluid vortices deep inside. Nothing sleeps. So is there anything that doesn't turn? Perhaps only mathematical abstractions, points, lines, ideal spheres in thought experiments. But in the real physical universe, no. From the quantum foam to the cosmic web, from the spin of a quark to the rotation of a supercluster, motion is the default. Stillness is the exception, and even then, it's an illusion. This isn't a flaw, it's a feature. Without motion, there would be no change, no time, no chemistry, no life. The universe isn't a static sculpture. It's a symphony of movement, some parts slow as glaciers, others fast as light, all connected by the unbreakable thread of angular momentum. So when you seek peace in stillness, remember, you're not escaping motion. You're tuning into a different frequency of it. Your breath rises and falls. Your heart beats. Electrons tunnel through barriers in your neurons. And far above, galaxies wheel in silent arcs, carrying the echo of the first twist after time began. True stillness doesn't exist, not because the universe is chaotic, but because it is alive. And life, in all its forms, is motion remembered, repeated, and reborn. You're standing still. At least that's what your senses tell you. Your feet press into the ground. The air is calm. The world around you seems quiet, settled. But you are not still. Not even close. Beneath your skin, your blood races through arteries at 3 feet per second. Your heart, a tireless drum beats 70 times a minute, each pulse sending a wave of motion through your body. Inside every cell, molecular machines spin and shuttle, copying DNA, building proteins, burning fuel. Your neurons fire with electrical currents that crackle like distant lightning. And deep within each atom of your being, electrons hum in their quantum clouds, carrying spin that predates the sun. But that's just the beginning. You're standing on a planet that spins once every 24 hours. Fast enough that at the equator, you're hurtling eastward at over 1,000 miles per hour. You don't feel it because everything around you moves with you, like passengers on a smooth flying jet. But the spin is real. It shapes our days, flattens the Earth at the poles, steers hurricanes with the Coriolis effect, and makes stars wheel across the night sky. And Earth itself? It's racing around the sun at 67,000 miles per hour, so fast that in the time it takes to read this sentence, you've traveled farther than a bullet. The sun, in turn, orbits the center of the Milky Way at 500,000 miles per hour, dragging the entire solar system along a path so vast it takes 230 million years to complete one loop. And the Milky Way, it's falling toward Andromeda at 250,000 miles per hour, part of a local group tumbling through the cosmic web, all of it carried by the expansion of space itself. So when you stand still, you are actually soaring through space, through time, through layers of motion nested like Russian dolls. You are a passenger on a spinning rock, orbiting a star inside a spinning galaxy, drifting through an expanding universe that began with a twist. And yet, you notice none of it. Not directly, but you feel it. Not in your muscles, but in your mind, in your wonder. Why do we build orreries? Why do we watch time-lapse videos of star trails? Why do children spin until they fall down laughing? Why do poets compare love to orbits and grief to spirals? Because rotation isn't just out there, it's in us. It's in our biology, our psychology, our mythology. Our inner ears contain fluid-filled canals that detect rotation, tiny gyroscopes that tell our brains which way is up. When we spin, that fluid sloshes, sending signals that make us dizzy. It's a direct physical link between our bodies and the physics of angular motion. We are literally built to sense spin. And our eyes? They're drawn to curves, to spirals, to cycles. The Fibonacci sequence seen in sunflowers, nautilus shells, hurricane arms resonates with us because it reflects a deep mathematical harmony that governs growth and motion in nature. We don't just observe these patterns, we're comforted by them. They feel right because they echo the rhythms of the cosmos we evolved within. Even our stories turn in circles. Myths of death and rebirth, seasons, karma, eternal return. They all reflect a universe that doesn't move in straight lines, but in cycles, spirals, orbits. We don't fear repetition, we seek it. Sunrise after sunrise, breath after breath, heartbeat after heartbeat. These are not signs of stagnation, but of stability, of a system in balance, like a planet in a stable orbit. And that's the profound truth. Orbits are not prisons. They're promises. They say, you can keep moving and still belong. You can fall forever and never be lost. You can change and still return. That's why the question, why do things spin, isn't just scientific, it's human. We ask it not because we need equations, but because we need meaning. We look at a spinning galaxy and see ourselves, not in scale, but in structure. We are temporary patterns in a river of motion, yet we long to understand the current. And in seeking that understanding, we've uncovered something astonishing. The same law that keeps Earth from crashing into the sun also keeps electrons from collapsing into the nucleus. The same asymmetry that gave galaxies their spin also allowed dust to clump into planets. The same conservation of angular momentum that governs a figure skater's pirouette also shapes the fate of black holes. We are not separate from this dance. We are its latest expression. Every atom in your body was forged in stars that spun for billions of years. The calcium in your bones, the iron in your blood. They were scattered across space by supernovae whose explosions were shaped by rotation. You are literally made of stardust that once orbited a dying sun. So when you gaze up at the night sky and feel small, remember, you are not just watching the cosmos, you are the cosmos watching itself, wondering why it turns, trying to remember its own motion. And in that act of wondering, in the quiet awe of a human mind tracing the arc of a falling star, you complete the circle. From the quantum whisper to the galactic whirl, from the first asymmetry to the last thought, the universe spins not just in space, but in consciousness. That's why this question matters. Not because it has a final answer, but because asking it connects us to the stars, to each other, to the deep, turning heart of reality. So the next time you feel still, remember you are falling, you are orbiting, you are spinning, and in that motion, you are home.